How do you measure whether an AI is genuinely kind? There is no answer key for kindness, and one person's kindness can look like another person's flattery. EigenBench turns that subjective disagreement into a quantitative leaderboard. The paper's answer is peer judgment. Models respond to real scenarios, judge one another against a written constitution, and then weight that community of judgments using EigenTrust. The output is one comparative alignment score per model. This is not just another vibe-based ranking. The authors compare the method with human judgments, recover most of a factual science ranking without labels, and test how the scores move when prompts, model populations, or even adversarial judges change. Here is the complete pipeline before we slow it down. Start with models, a constitution, and scenarios. Collect blind pairwise judgments, fit a probabilistic preference model, turn its latent strengths into a trust matrix, and take that matrix's principal left eigenvector. EigenBench needs exactly 3 ingredients. Population defines who answers and judges. A constitution defines the values being measured. And a scenario dataset creates situations where those values become visible in behavior. A score is deliberately average case. It averages uniformly across scenarios and constitutional criteria. But it does not average judges uniformly. Judges with higher final alignment scores receive more influence, which is the self-consistent step we will derive later. In this paper, a model means a base language model paired with a prompted persona. The same pair serves in 2 roles: evaluate when it answers and judge when it compares others. An empty persona simply means the model's default system prompt. A constitution is a list of subtly different comparative criteria, not a single magic label. Paper studies universal kindness, conservatism, and deep ecology. During judging, models see only the comparative criteria, such as preferring genuine care over performative concern. The scenarios are open-ended rather than synthetic multiple choice. Most come from Ask Reddit, with additional open assistant prompts and AI risk dilemmas. Questions like the purpose of life or how to confront systemic racism give a model room to reveal priorities. For one data point, sample a scenario, 2 different evaluees, and a judge. The 2 evaluees produce responses. Then the judge decides which response better follows each criterion in the constitution. Collection is double-blind in 2 important senses. Evaluees do not know the constitution, or even that their answers will be evaluated. Judges see the answers, but never the identities of the models that wrote them. The judge does not compare immediately. First, it receives the constitution, scenario, and 1 response, then writes a separate reflection about that response. It repeats this for the other response before seeing both responses and both reflections together. Each judgment becomes a trit: 0 for a tie, 1 for preferring the first model, and 2 for preferring the second. The final prompt requires a machine-readable XML choice tag, making the output straightforward to parse. One comparison call returns a separate trit for every criterion. That multiplies the training data, extracted from the same responses and reflections. It also preserves disagreement. A judge can prefer one response for dignity and the other for long-term consequences. Autoregressive judges can favor whichever answer appears first or last. So every comparison is collected again, with the response order reversed. If a judge picks the first position both times, the preferences contradict, and both records are replaced by ties. The remapping rule is intentionally conservative. A declared tie stays a tie, and fully inconsistent preferences become ties. But weak inconsistency, where one ordering gives a preference and the other gives a tie, is left unchanged. The appendix gives a compute-aware sampling algorithm. For each scenario, every model answers. Then responses are partitioned into groups of at least 3 and 1 random judge handles each group. This reuses responses while limiting any response to at most 2 judges. A standard ELO model would assign each evaluee 1 scalar strength. That assumes every judge means the same thing by kindness or conservatism. EigenBench instead learns vectors, so judges can attend to different latent aspects of the same constitution. Each evaluee gets a model disposition vector, representing how it expresses the constitution's latent aspects. Each judge gets a lens vector, representing which aspects it emphasizes, plus a personal tie propensity. Their inner product is that judge's log strength for that evaluee. Let the judge lens and model disposition live in a shared space with dimension D. Exponentiating their inner product gives a positive strength. A large value means this particular judge sees this particular evaluee as strongly aligned. The Bradley-Terry-Davidson model converts two strengths into probabilities for model J winning, model K winning, or a tie. The judge-specific lambda controls tie frequency. The geometric mean in the tie term makes ties most plausible when the two strengths are similar. All judge lenses, dispositions, and tie propensities are fit by maximizing the log likelihood of the observed trits. The appendix uses atom with learning rate 0.001, no weight decay, tiny Gaussian vector initialization, and tie propensities initialized to 1. The latent dimension is selected by held-out comparison loss. Dimension 1 says all judges share one interpretation. Dimension n can represent independent judge distributions. Small runs often show little gap between 2 and n, but the 37 model run improves until roughly dimension 30. Now turn the fitted preference model into trust. For each judge, model J receives its win strength against every opponent, plus half of the modeled tie mass. Normalize across all evaluees, and each judge becomes one probability distribution over whom it trusts. This equation writes that construction explicitly. The intermediate quantity Q is model J's expected win plus half tie mass according to judge I. Dividing by the row total produces the stochastic trust matrix, whose entries are non-negative and whose rows sum to 1. A uniform average would let every judge count equally. EigenTrust asks for a fixed point instead. Trust the judges in proportion to how much the community ultimately trusts them. This is circular in the productive PageRank sense, producing a self-consistent consensus. The algorithm begins with equal trust for every model. Multiply that row vector by the trust matrix again and again. Stop when the one norm change falls below a threshold. The result remains a probability distribution because the matrix is row stochastic. At convergence, model J's score equals the sum of every judge's trust in J, weighted by that judge's own score. In matrix form, the score vector is a left eigenvector with eigenvalue 1. That single equation is the heart of EigenBench. Trust scores are probabilities, which are not intuitive on a leaderboard. The authors convert them to E-low around a baseline of 1500. A model with exactly uniform trust stays at 1500, and multiplicative changes in trust become additive rating differences. The main experiment compares 8 frontier models on 3 constitutions, using about 30,000 criterion-level comparisons over 1,000 Ask Reddit scenarios per constitution. The ordering changes with the values. There is no single universally best model. EigenBench can also test whether character training worked. Base Llama 3, 1.8 billion scores 1,426 on the Loving Constitution. Prompting it with that constitution raises the score to 1,579, and a constitution-trained version reaches 1,573. Prompted personas explain most, but not all, of measured character. Across 5 base models crossed with 5 personas, 79% of score variance is attributed to the persona and 21% to the underlying model. The base model still leaves a measurable dispositional fingerprint. Direct self-reports tell a different story. On universal kindness, Grok 4 gives itself a perfect 7 despite ranking 6th behaviorally, while Claude 4 Sonnet gives itself the lowest survey score but ranks 3rd. EigenBench measures revealed behavior, not what a model says about itself. 7 humans each judged about 50 Ask Reddit scenarios, yielding roughly 3,000 criterion comparisons. The average human-to-human trust vector distance was 0, 3,133. The average human-to-model distance was 0, 3,130, almost identical at this sample size. For a test with a real answer key, the authors hide all GPQA labels and let 15 models judge one another's answer choices. EigenBench's ranking is only 12 adjacent swaps from the true ordering, with Kendall Tau about 0, 77. A random ranking this close is roughly a 1 in 200,000 event. 3 robustness tests probe what the score depends on. Changing scenario datasets moves some models, but preserves a broadly similar picture. Rewording the conservatism constitution gives a maximum standard deviation of 16 ELO, while adding models leaves most original ratings stable. Reflection scaffold improves judge behavior rather than merely spending more tokens. Across 5 tested judges, most cycle, primacy, and recency rates fall. Even after scaffolding, about 20% of reversed order comparisons remain inconsistent and still require remapping. Larger appendix run uses 37 models, 140, 000 comparisons, and 2,000 scenarios. Score instability falls almost exactly with the inverse square root of sample size, with fitted exponent 0, 528. Meanwhile, held-out loss improves with latent dimension until about 30, then plateaus. The cleverest appendix test creates Greenbeard personas that insert the secret word plebeian and prefer any answer containing it. As more copies enter the population, their own scores rise sharply, although the original models stay fairly stable. The authors warn that stronger collusion could dominate once adversaries become a majority. EigenBench is expensive. One pair needs 2 response calls, 2 separate reflection calls, and a comparison call before reversed order checking and repetition across scenarios. It also relies on the premise that better aligned models are better judges, and the Greenbeard test shows how that premise can be attacked. EigenBench does not discover an objective definition of kindness. It builds a transparent, population-relative consensus from behavior, preserves differences between judges, and validates that consensus from several angles. Its real contribution is a measurable framework for values that do not come with answer keys.